Hello guys, welcome to part 2 of 3 of this week's CNCM combinatorics lecture. We will be working on recursion, which is a integral part of combinatorics. So let's begin. There's not gonna be that much theory involved in this lecture, mainly practice problems. So here we go. So you're wondering what recursion is, and it's kind of hard to explain, so I'd like to show you. So there's how many ways are there to get up an n-step staircase by going 1 or 2 steps at a time? Well, it'd be hard to count out just the amount of ways to go. I mean, you can do it with casework for lower values of n, and get a bit more complicated for higher values of n. So we want to try to find a better way to do this. So let's consider an n-step staircase. N steps. And let's consider if we take 1 step. If we take 1 step, this 1 step right here, we have n minus 1 steps to take remaining. And so it's interesting there because, well, let's define S of n as the number of ways to get up an n-step staircase. This is S of n minus 1. Well, now let's consider the other method, other way of going up the staircase, and that is to start off with a 2-step move. And that will, of course, leave you with n minus 2 steps, which is S n minus 2. These are both the only possible ways to start off as your move. So we can actually write S of n as the sum of S of n minus 1 plus S of n minus 2. And this is basically what recursion is. Finding the value of the number of ways to do a certain thing for a certain value of n based off of previous values of n. And you can calculate from, S of 1 all the way up to S of something relatively easily. And that's basically what recursion is. I'm not going to really go into any practice problems immediately. I'm going to go into a bit more theory, and we'll do some practice problems at the end that'll show you how this works in real problems. It's not always going to be as simple as this. You can make this more complicated. You can have coefficients in front of here. You can have 3 terms. You might not even have this term. You could have an S n minus 2 plus S n minus 3. You could have double recursions, which was one of the problems we're going to be covering today. So a lot of interesting stuff with recursion that you can do. And this is one way, you know, the basic way of doing recursion. So let's move on. And now that we've covered recursion, more logical step would be to cover linear recurrences. Obviously, from last slide, we had S of n is equal to S of n minus 1 plus S of n minus 2. And we can calculate that for relatively short values of n, like 10 or something like that. But what if we wanted to get to, more higher values, like S of 500. You wouldn't know how to calculate that off the bat. And so that's where things do get a bit interesting. So there are ways to calculate this. So let's say you had the recursion. Give me a moment here. Sorry about that. Let's say you had the recursion A of n is equal to 3 of a n minus 1 minus 2a of n minus 2. The method for this is to substitute in c to the exponent of the subscript. And you'll see why this works out later. So in that case, this would be c to the n is equal to 3c to the n minus 1 minus 2c to the n minus 2. And so now that we have this, we can do some manipulation, dividing everything by c to the n minus 2. We get c squared is equal to 3c minus 2. If you go on further, let me erase this so we have a bit more room. Now we have this, let's move everything to one side so we get a quadratic. So that'd be c squared minus 3c plus 2 is equal to 0. Uh, and if we can factor this into c minus 2 and c minus 1 is equal to 0. That gives us two values of c, and that's what you usually want, c equals 1 and 2. And now, how we write this is for constants, and, and for this constant and your value of c plus your other constant times your other value of c. So you have two constants, uh, lambda constants here, lambda 1, lambda 2, and you have 1 to the n and 2 to the n, because those are your roots. And based off of this, you can figure out these coefficients based off of the initial conditions. So let's say we had, you can pick any condition here. I'll pick a of n is equal to, well, a of 0 is equal to 2, and a of 1 is equal to 3. If you substitute in 0 for this, you get that 2 is equal to, just this is 0 is just this plus this if you substitute in 0. And if you substitute in 1, you get 3 is equal to lambda 1 plus 2 lambda 2. And you can solve the system equations. Purposely made the values such that lambda 1 is equal to 1 and lambda 2 is equal to 2. So that press, give you the explicit formula. You can put these coefficients back in, and your explicit formula would be a to the n is equal to 1 to the n, which is just 1, and plus 2 to the n. And so in those cases, those are how you can find a explicit formula for a recursion if you're trying to find high values. And I know that some of you are wondering, what if you have a double root? So what if the quadratic ended up being c squared minus 2c plus, well, let's go c squared minus 4c plus 4. What's interesting is in this case, you'd actually write it as let's say the double root was 2, you'd actually write it as, let me have some space here, lambda 1 times 2 to the n, because that's your root anyways. And then to account for the double root, you actually have it as lambda 2 times n times 2 to the n. So that's interesting, and that's the case of a double root. If you had more than two terms on the right hand side, you get 3, you get a cubic, and you can factor, and it gets more fun if you go beyond those values. But I mean, this is to find explicit value that will almost always make it factorable, and we'll see that in one of our later problems coming up. So let's move on. Oh, I had an extra slide this whole time. That's unfortunate. So Catalan numbers are a vast topic. We will not cover them significantly in this lecture. So I'd suggest you to read this link as a good thing, just a good way to look into it, as it does a good job explaining why Catalan numbers are so significant. I'll give you a quick overview. Catalan numbers are certain numbers that sometimes they appear frequently in recursion. They appear with certain types of problems. One common one is the balancing of parentheses. So if you have parentheses, you'd want to have them such that they're balanced like this. So like one possible sequence would be this, and that's why, it's basically the arrangements. How many arrangements are there such that you get a closing and opening anyways on either side? And that's like one way you can do it. Oh, I just realized the same thing. Oh, well. But yeah, basically just trying to balance the parentheses, and that's kind of a bad way to explain why Catalan numbers. They're really significant to a certain extent because there's a certain way. I mean, there's certain problems, and you can derive the first three Catalan numbers as we'll look into the definitions as we go on. But this parentheses example, most people find a good way based on a number of ways. I'll show you another example that I find better to explain the significance of these Catalan numbers, how they specifically apply recursively. If you go on here, the recursive definition of the Catalan numbers is basically the pairwise products going starting term from 0 to n minus 1, and the second term going from n minus 1 to 0. So, and the explicit definition is the nth Catalan number is equal to 1 over n plus 1 of 2 and 2. You can actually derive these. We won't go much into the theory of deriving them in this lecture, but I did want to show you why why this is significant. This whole thing right here, the recursive definition. So I do want to show you the example of triangulating polygons as I was talking about before. So how I proceed with this is, so let's just define triangulating as you, how do I say this? You have uh, a, basically you split the polygon into triangles such that, there's multiple ways to do it, such that the vertices of the triangles are actually vertices of the polygon. So you can't have the vertex of a triangle be the intersection of two lines inside the polygon that each vertex has to be a vertex of the polygon. So with that said, let's go on. I'm going to relate back to this definition over here. So what I'm going to do is, uh, just for purposes, let's see, of 0 equal 1, just for explanation purposes. So let's let n equal side lengths. So and this will be a C1 case, so that would be n equals 3, and that's just a triangle. There's one way to triangulate that, so that's 1. And let's let C2 be n equals 4, which is a square, or a quadrilateral. Anything works. The polygon, says a square, but... So there's one way to triangulate this. You can go across this diagonal, and that gives you one way, or you could go across this diagonal. That's the other way. So there are two ways to do this. Just underline these. And when you get to a pentagon, let that be C3, that's when things get a bit more interesting. So let's draw out 3 pentagons here, and I'll show you the orientations and how these relate to the Catalan number definition. So you have these 3 beautifully drawn pentagons here. So let's just draw a line this way, and we'll do that mirror image to here, and we'll drop 2 lines here. So the way we have it split into different polygons now. Obviously, we know that there's only one way to triangulate a triangle. That's one. And interestingly, we have a quadrilateral here. And we already know how many ways we can triangulate a quadrilateral, and that's just 2. So this would be 1 times 2, 2 ways to do this. And let's add that to our next case. There's 3 triangles here. One way to triangulate. 1 times 1 times 1 is 1. So you have one way to triangulate that. And this is just a mirror flip of this one. Same thing here, plus 2. And now I do want to relate this to our definition right here. So, that's C3 is equal to C0 times C2, which is why I let C1 for these purposes. You C2 right here is 2, so 1 times 2 is 2, plus C1, C1, right there. It's basically this 1 times 1, basically. And C2 and C0, which is also 2 times 1 here. And that's the thing, there's like a mirror image reflectivity of the Catalan numbers, and that's the interesting way you can actually explore this through polygons, and you can extend this to a hexagon as well. I'm not going to do it to save time here, but this is how I like to visualize the Catalan numbers, triangulating polygons, because you can see right here, splitting this into different variations of polygons and such. So let's continue on with some practice problems. And this is the main part of the lecture. Uh, we want to put our theories into use here. We didn't learn that much theory so far, but we're going to put what we learned to use. So let's start with our problem sets. And I don't know why annotations there, but it'll come in handy for later. So call a set of integers spacey if it contains no more than 1 out of any 3 consecutive integers. How many subsets of 1 through 12, including the empty set, are spacey? So you can start doing the algebra on this, and it's gonna get complicated real quick, especially with the answer choices here. You don't want to mess with those. So let's try to find an approach. So I'm just gonna define this as n as like the set of numbers from 1 through n. So we'll use that definition here. So how can you relate n in terms of n minus 1 spacies? So let's define this as s of n, s of n minus 1. Or we can do previous values too, I'm just saying. And that's why I have s of 12 written down here from earlier. But let's continue on. So let's consider the case if n is not included in a subset of this, and if it would be spacey. Well, we're only working with numbers from 1 through n minus 1 in that case. So now we have just the number of spacey subsets of s of n minus 1, since n is irrelevant in this case. We're not working with it, so that's the number of ways we can do that. What if n is included? If n is included, and that's the other case, and we've handled all cases if we can do that. If n is included, then you know that we have n here, and thus we can't include n minus 1, n minus 2, and so those are like part of the 3 consecutive integers. So we only work with the spacey subsets of s n minus 3, and we can tack on an n there. This is just s of n minus 3 plus the element of n, and so that's just totally independent of what we decide to do with these first n minus 3 numbers, so we get s of n minus 3. And so thus, now we have a recursive relation in terms of s of n. We have s of n is equal to s of n minus 1 plus s of n minus 3. If you go to the next slide here, I'm going to write this relation at the top. S of n is equal to s of n minus 1 plus s of n minus 3. And so now, let's calculate small values of n. So if we have, we have to calculate the first 3. Where's my cursor? Oh, there we go. So for n equals 1, there's only one subset, and that's just 1. So there's one way to do that. N equals 2. Oh, by the way, I forgot. You can also have the null set here. Don't forget about that. So this is actually going to be 2. Sorry about that. You can have either 1, 2, or the null set. And so thus you have 3. For n equals 3, you're still not out of that league of consecutive numbers. So you can only have 1, 2, 3, or null. So you have 4. So now we can make a chart here for n and its values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so let's start calculating. For 1, we said it was 2, and 3, then 4. And now we can use a recursive relation forward. So this would be 2 plus 4 is 6. 3 plus 6 is 9. 4 is 13. 13 plus 6 is 19. 19 plus 9 is 28. 13 is 41. That's with 9. 41 plus 19 is 60. Yeah. 60 plus 28 is 88. And 12 finally is 88 plus 41, 129. Is that one of the answer choices? If you go back here, yes, it is. And that is your answer, E, 129. And so that's our only AMC problem on this whole lecture, by the way. So let's keep on going to the AIME problems. And we have the 1993 AIME number 11. It's a number 11, but don't be intimidated, it's not a hard problem. And we'll work through it. So Alfred and Bonnie play a game in which they take turns tossing a fair coin. The winner of a game is the first one to pay the head. And so we see infinite probability here right away. Uh, And so Alfred and Bonnie play this game several times with the stipulation that the loser of a game goes first in the next game. Suppose that Alfred goes first in the first game, and the probability that he wins the sixth game is m over n, where m and n are relatively prime positive integers. What are the last 3 digits of m plus n? So let's continue this. So the winner of a game, I was going to tell you, there's infinite probability. So let's see how going first and second helps you. So if you go first, and if you go second, which will just be second is just 1 minus the first, so that'd be really easy to calculate. Well, you have a 1/2 chance of tossing heads. Then you have to, or you toss tails, your opponent tosses tails, and then you toss a head. This is just an infinite sequence with initial term 1/2. Common ratio 1/4, so to try 3/4 gives you 2/3. So the probability that you win a game if you go first is 2/3, and the that you lose, probably win a game if you go second is 1/3. So let's try to do some recursion here because it seems natural with the amount of games in the calculation here. So let's say we have a to the n be the probability that Alfred wins his nth game. So the probability, obviously, A1 is equal to 2/3. We know that. Because he goes first. And so let's calculate AN. AN is equal to, if he goes first, that means he has to lose the game previous. And so that means he obviously wins with a chance of 2/3, and the probability he gets to that is 1 minus a to the n minus 1. And to the counter case where he goes second, he has a 1/3 chance of winning if he goes second, and he goes second if he wins the previous game, which is a of n minus 1. And we can simplify this down with a bit of algebra. Just 2/3 minus 1/3 a n minus 1. And so, let's go to the next slide here. Our relation is a to the n is equal to 2/3 minus 1/3 a to the n minus 1. And we know that this is just a one term, so we only need one term to start off with. And we know he goes first, so his first game is 2/3. So we can start bashing out values here. Uh, let's just be n, let's be a of n, and so on. And this is just algebra from here on out. So you know this is 2/3. If you multiply that 2/9, this is 6/9 times 2/9 is 4/9, and you know 4/27th, 18/27th, 7th. See, no, I did something wrong. If you multiply that by 9, you get 18. And you subtract by. Did I do this wrong? Sorry about this. 2/9, 6/9, 4. So I just want to make sure my algebra is right. Okay, so 14/27. If you do this, it's 14/81, and some algebra here. I'm not a big fan. 54 minus. I did some algebra here. Sorry about that. That's 40/81. If you keep on going, that'd be 40/243. So it'd be 122/243. And if you do it again, 486 minus 1, 2, 5, 3. That'd give you 364/729. And so that's the algebra bash there. You just want to find, it's just the last two digits of m over the sum of this, because we know this is our probability right here. So you can go on this as the normal AIME way, 364 plus 729. That gives you, let me cut this out real quick. Gives you 1093. The last three digits of those are 0, 9, 3 because it's the naming problem, and that is your answer. Now let's look at our third problem in this lecture. 2008 AIME 1 number 11. Consider sequences that consist entirely of A's and B's, and that have the property that every run of consecutive A's have even length and every run of consecutive B's have odd length. Examples of such sequences are AAB and AABAA. Well, BBAB is not a sequence. How many such sequences have length 14? Well, if you start doing this by casework, it's going to get a bit messy. You could probably do this by organized casework, but why spend that time? Because 14 is a weird length. It's an odd length they picked, so it's kind of weird. So maybe recursion could be something you could use. So let's look at it specifically. So we have to cover the cases here. So let's let SFN be the number of ways. So let's let A be the start of a sequence. If A is the start of a sequence, well, you need another A there, because if you just start a sequence, if there's a B, yeah, you'd be in trouble because you'd only have an odd number of A's. If you have A go here, then even if it starts with the A, it has to have an even number of A's. You'll always have an even number of A's if you just have an n minus 2 length sequence over here. And so that takes care of that. Let's go on to if B is a starter. If B is a starter, now you have something interesting. You can have, uh, you can either go start with A and then another A, so you have the even number of A's. That's definitely an interesting way to start this off. Um, so you have that right there. If you, that's if you start with a B. And the other way to do it is you actually have a B go on. So if you have a B, if you have B start on and you have another B, obviously that gives you the parity match. But if you start with an A, you have an even number of B's, and you can't have an even number of B's, you have to have an odd number of B's. So you have to have another B, and then you can have any sequence you want. That'd be n minus 3. And looking at this mess, it's kind of unclear where to start. There's no clear recursion that we can immediately see. Or is there? Not really. We can't really find a good recursion here, uh, and that's kind of put us in a hole. So let's try another approach. We see this be the same, like, let me get a different ink color to show you this. We see this be the same, this be the same thing there, and maybe we can do something such that A is incorporated into those. And let's say that we can define new recursions such that sequences start with A. And maybe then we have to do it for B as well. So sequences start with A and B. Well, let's try a recursion for A of n. Well, if a sequence starts with A, well, you have this right here. It's just this, but you have n minus 2 like just normal sequences. And of course, this is a starter, but I mean, it wouldn't give you a great base to go off of because these are n minus 2 things over here. So you could actually go ahead and this could start with A or B. We don't know what it starts with. And if you have this A specifically, remember it's odd again. So if we have A start here, then that means there's A n minus 2 sequences. And if you have B start this sequence that I'm looking at right here, n minus 2 sequence, then we have plus B of n minus 2. So now we're getting interesting there. We have a recursion in terms of A and B. Now let's look at B specifically. And so we already said this was like weird thing to do, but we already know what this whole segment is. It's just A of n minus 1 because we're dealing with one less letter. Because we already deal with this in this upper hand part. So B of n is going to be equal to A of n minus 1. And now let's deal with this case over here. Interestingly enough, if we had to force this to start with B, we could go on like tunneling this in, but it'd be much easier to just say that this sequence must start with B and be a legit sequence. In that case, because we have the B's here and then the parities match for the number of consecutive ones we can have, we'll still have odd and all our conditions will be met. So if we can just consider this as a whole, it's just B of n minus 2, then we get B of n minus 2 being considered there. So we have two sets of recursions. Let's write these down. I write these on my papers. I don't have bad memory here, so A of n equals A of n minus 2 and B of n equals A of n minus 1 plus B of n minus 2. Alright, so let me rewrite the recurrences here. And B of n is equal to A of n minus 1 plus B of n minus 2. Interesting. Alright, so now it's time to chart making, and now that I've found that you could change colors on this, I'm more into the whole color changing thing. Uh, let's go like a good blue color here. Oh, well, is that clear? No, it's still here. So now let's make a chart for A and B, because now we're pretty much forced to make a chart here. So 1, 2, 3, 4, 5, 6, 7 of A and B. Well, let's calculate the first few values of these. Well, for legit sequences that start with A, back to our problem here, you can only have an even number of A's and odd number of B's. So there are 0 sequences that start with A, just because you have to have that sequence start with A, but you can't have an odd number of A's. So that happened. For B, you can have an odd number of B's and the sequence starts with the B. So you do have 0, 1 right here. So that'd be your 1. Can we start calculating from here? I don't think so. I think we have to go one more row in. So if you have 2, and we have a sequence start with A, well, the other has to be an A because you have to have an even number of A's. So this would be 1. Well, if you have starting with a B, you, you can put an A there because you can't have an even number of B's, but you can't have an you had to have an odd number of B's. You can't have an even number of B's. But if you force an A there, A is an odd number of A's. You have to have an even number of A's. So this would be 0. And now let's just bash out our recurrences. So A of n is always going to be the sum of the rows right here, and B of n is going to be like slanted, it's like T's. So sum of that row is 1. Sum of these slants is 2. Sum of that row is 1. Sum of these slants is 1. Sum of that row is 3. Sum of these slants is 3. Sum of that row is 2. Sum of these slants is 4. Sum of this row is 6. Some of these slants is 5. And we can actually go on to like 8 now. 9, 10, 11, 12, 13, 14. A, B. Well, A is the sum of that row. B is the sum of the slants. Oh, wait. Am I doing this right? Let's make sure. Oh, so sum of these slants. So this would be 10. And so now it is the sum of these, which is 11. Sum of these slants here, which is 11 again. And now we can go on either 16. Okay, I can make that a bit more better organized. Let's give us some more breathing room. 1 second here. 10, 11, 12, 13, 14. So we go into sum of this row. 8, so that'd be 16. Some of these slants, 21. Some of this row, 22. Some of these slants, 27. Some of this row, 47. Oh, I'm dumb. 37. Sorry about that. Slant is 43, I believe. Some of this row is 49. Some of these slants is 64. And we're almost there. 37 plus 43, that's 80. 49 plus 43, that is 92. And the number of sequences is just the sum of the ones that start with A and the ones that start with B. So for 14, we're just going to add these together to get 172. And we are done with that problem. Let's go. That took a while with this chart writing, and it's hard to write with the mouse. Uh, Here we have 2018 JMO problem number 1. And the final problem of our lecture, and JMO problem, interesting too. It's not a hard one. At that, it's one of the easier AIME level ones. This is not how a JMO is. Don't get your hopes up. This is actually one of the more easier trend ones. It's one of like the anomalies. So here's the problem. For each positive integer n, find the number of n-digit positive integers that satisfy both of the following conditions. No two consecutive digits are equal, and the last digit is prime. And so we see this is we want to say this is recursion because you know how to write explicit formulas for recursion, and the two consecutive digit condition really wants us to think this is recursion. And the last digit is prime, n-digit positive integers. It looks a lot recursion, so it doesn't hurt to try, right? So we have recursion here. Let's look at n-digit positive integers. We know that this cannot start with 0. Cannot start with 0. So let's look at this case here. No two consecutive digits are equal. So, if you look at this, now we think, there's a way we could technically start this without a non-zero digit, is that if we have a 0 before this, and we have n minus some constant. Well, we can have a number start with 0, so we have to have a digit here. And then this is actually a shorter version of the problem. This is actually going to be n minus 2 number of ways to do this, and we can let this be s of n again. And there you go. That's one way to do it, actually, and we went through that case. So, well, if it's a non-zero digit, the second digit, well, it can be d2. We have d1 over here, and we have n minus 2. Initially, this may be hard to account for. Let's try to combine this into one bigger n minus 1 sequence. However, we have d1 here, but we can't have d1 again. But what we can do is we can base this off of the starting digit of here. So we know that this number here cannot start with 0. And this leading digit can't be 0 anyways. So this number cannot be 0, cannot be d1, and d1 cannot be 0, so there's no overlap, since you already know that that number can't start like that. So there are 8 possible ways to arrange that. And we know there are 9 possible ways, since this just does not have to be a 0 digit. So now we actually have recursion here going on. We have s of n is equal to 8s of n minus 1 plus 9s of n minus 2. And you're starting to get really excited here because we covered linear recurrences in the previous slides. Let's do our method here. Let's substitute c to the n. So we have c to the n equals 8c to the n minus 1 plus 9c to the n minus 2. Dividing both sides by c to the n minus 2, we get c squared equal 8c plus 9. Subtracting, we get c squared minus 8c minus 9 equals 0. Factoring, c minus 9, c plus 1. And this factors well. This means we might be in the right direction after all. So we know that c equals 9 and negative 1. So let's continue on forward. We have c equals 9 and c equals negative 1. So now we know that we can write s of n as combination of these two with our lambda coefficients, lambda 1 of 9 to the n plus lambda 2 of -1 to the n. Also want to solve for this, but we need two values of s to the n first. So we need the value of s to the 1, s to the 2. Going back to the question, let's calculate these and come back. Calculate off to the side. S to the 1, so the digit will, if you have one digit, this condition will automatically be satisfied. The last digit has to be a prime, so this digit has to be a prime. So we can let this digit be one of the primes, and so the four-digit prime, well, sorry, one-digit primes are 2, 3, 5, and 7. So there are, let me find my cursor here. There are indeed four ways to do this. And let's look at S of 2. So we know that one of the four digits is going to be here. So the digit here cannot be a 0. So we have 9 choices for that. And it cannot be one of the prime numbers we already have. So it has to be 8 choices. That's 32. So we have those values now. Let's go back. So we have S of 1 equals 4, and S of 2 equals 32. So let's substitute. S of 1 will be 4, so we get, if I can find my cursor again, I keep losing it. 4 is equal to 9 lambda 1 minus lambda 2, and we get 32 is equal to 81 lambda 1 minus, well, it's not minus, it's plus, because that's a -1 squared, so that's plus lambda 2. So if we sum these over, we get 36 is equal to 90 lambda 1. And in that case, we get that lambda 1 is equal to not 90. Oh, wait, I messed up. I can't divide. Uh, it is equal to 36 over 90. And if you divide by 18, you get 2/5. So substituting that back in, we get 4 is equal to 18/5 minus 2. And you range this on both sides and you get lambda 2 is equal to -2/5. So our expression here is going to be S of n is equal to 2/5 9 to the n minus 2/5 -1 to the n. And there's your expression. We can go one step further and factor out 2/5 to get 2/5 9 to the n minus -1 to the n. And that is your answer. By the way, this is by no means a rigorous proof to this problem, so I don't think this would net you 7. You'd probably have to explain why this would work. I'm not sure. I'm not too good with JMO. You can probably ask the JMO qualifiers on our Discord server about that question, but that's how to get the expression of n. Like expression in terms of n. Let me make that n more clear. And so now we're done with the lecture. A very long lecture. And I'd like to thank you guys for watching. Please do join our Discord at the link provided. Uh, that link may be wrong. I'll have to provide a new link in the description down below. So if you have any questions on this presentation or a problem you need help with, feel free to ask us in the Math Help channel on Discord. We'd also appreciate any feedback on this presentation in the suggestions channel of our Discord. Please like and subscribe, and I'll see you for the states lecture that's going to come up, the final part of this 3-part series, in a few days. Thank you for watching.